Welcome to Talk Universe. I'm your host, Sir Charles Schultz. Our show is all about science and technology and how it affects our society and the people in it. Tonight's show is a special show which consists entirely of questions and answers. Now, I maintain a fair presence on my website and on social media, and I am constantly asked numerous questions on science, physics, electronics, and various subjects. And tonight is going to be a show completely dedicated to answering the questions that all these people have, all my friends and listeners and contacts. So it should be a lot of fun. We're going to cover a wealth of subjects ranging across the spectrum of science and technology. And we're going to look at answers that sometimes seem to be very hard to get, very clearly explained answers to simple questions about science and physics. We want to also have a shout out to our new listeners in Mexico. We've got quite a contingent growing there, as well as continued interest from Ukraine and Russian Federation. We have had approximately 600,000 page hits over the last 3 months on the site and many return visitors, so that's a very positive sign. I'd like to start out right away with my Singularity Watch, and the first item I have is that NanoWorks, a company, has produced light-emitting diodes on a flexible metal foil for the first time. Now, engineers at the Ohio State University are developing foil-based LEDs for portable UV lights, specifically for sterilizing drinking water and medical equipment. This is an interesting article that was in the Applied Physics Letters, the journal, and it describes how they created LEDs that will actually emit deep UV, very energetic ultraviolet light at the far end of the spectrum. They're licensing the technology to the industry now for further development. What this does is it allows people to create extremely efficient, energetic LEDs that create ultraviolet light that can destroy organic molecules. And normally the lamps that do this are heavy, made with mercury, and are difficult to get a lot of efficiency out of. So what they've got now is a process for making these on lightweight foil, which means that we can see portable water sterilization equipment very soon. Previous elements were for making this sort of ultraviolet were extremely bulky and delicate, and again, not very efficient. So we expect to see some real positive news on sterilizing drinking water and surgical tools very quickly. Here's another article. It's extremely interesting. There is a need for communication among nano devices and microelectronic devices, and we already have some pretty clogged bandwidth for a lot of things that communicate with each other. Bluetooth and Wi-Fi signals are pretty much filling up the band. So where do you go? And the answer is something called Terahertz Waves, or T-Waves. The concept is these are much smaller, much shorter wavelengths than microwaves, and a little bit longer than infrared light. So they're between radio waves and light waves on the spectrum. They're very difficult to detect and pick up. However, there's a fellow by the name of Joseph Jornet, who's a PhD. He's an assistant professor of the Department of Electrical Engineering at the University of Buffalo School of Engineering and Applied Sciences. And he received a grant for the U.S. Air Force Office of Scientific Research to develop a wireless communication network in the terahertz band. So what he's come up with now is a system that creates tiny antennas made of the material known as graphene and semiconductors. And it gives short-range, high-speed communications. So you can imagine files that take an hour or so to move from one computer to the other over traditional wireless methods being done in just a second or a few seconds. And this is what it's going to do. It creates the ability to make tiny sensors integrated into things that can communicate very easily back to a control system and monitor things like bridge damage or body temperatures or just about anything you can think of. So it brings communication, short-haul, very high-speed communication to devices. This is something we're definitely looking forward to in the near future here. Now here's something that a lot of us can appreciate. This is something they call thinking soil, and what it does is it repairs concrete foundations using bacteria that have been engineered to do the task. Skyscrapers often have foundations up to 20 feet thick and 200 to 300 feet deep. And that's to give them the stability they need, and that's an awful lot of concrete. And the problem is, in many places, thawing and mining and poor drainage and other things can happen that make the land subside. Now, concrete foundations protect to some degree against that, and that's what they're there for. But the problem is there are issues that can actually cause damage to the concrete as well and weaken it. Now, what happened is some British students have created a concrete repairing bacteria, and they have created this biocement, which is a material that uses the genetically engineered soil microbes to produce materials in response to changing pressure in the soil, and that will reinforce the land under the foundations. So, in effect, they are taking a bacterium, Bacillus subtilis, and adding it to the soil, and it makes an enzyme called urease, and the enzyme causes the urea to break down into ammonium and carbonate, and that changes the pH in the soil. That means that the calcium carbonate will accumulate at the cell surfaces, and when there's enough of it, you get a calcite deposit. In other words, it grows the concrete for you. So this process is being studied, and they're actually making it work. So pretty soon we would have something that will be able to, say, repair a foundation after an earthquake, re-solidify it. Thinking soil is something that's being made now, and it's in our future. So that's our Singularity Watch. We got some fascinating items there. Deep ultraviolet LEDs on foil for sterilizing water. Smart soil for fixing foundations that have been broken. And all of these advancements are happening at an ever-accelerating rate. The singularity, that hypothetical point where the amount of information grows so rapidly we can't predict what happens next, appears to be bearing down on us very rapidly. So let's get down to the questions and answers part of the show, and the first one is a simple physics question. We get these all the time. Is impulse the same as momentum? And this is from Israel Izzy. The answer is no. Impulse is the amount of energy or thrust that it takes over a duration of time to get something moving or to change its velocity. Momentum is the energy of movement that something contains. So it is a different thing. Impulse can be applied to give momentum to an object. That's the difference. There are a number of fairly simple properties that physics has that we work with all the time. And most of the answers for these things are simple enough to find. When people refer to mass, what mass literally refers to is a quantity of matter. And we have means of measuring it. Generally, we measure mass in kilograms or grams or some value such as that. And so the mass is truly the quantity of matter that something is made of, what it contains. When we talk about momentum, we talk about how much energy of movement that object has. We talk about velocity, we're talking about how fast it's moving and what direction it's going, and those two things together make up velocity. So with just a handful of very simple things such as this, we can describe just about everything about any system in physics. And it's very useful, very helpful to understand what these terms mean when we start talking about physics. And the big issue is physics isn't hard. Most people simply aren't familiar with the terms. Now here's an interesting one from Alex Sharma. And the question is, if I'm in a spaceship traveling at the speed of light and I try to walk forward in the spaceship, do I go faster than light? And the answer is no, because if the ship is traveling at the speed of light, your time is standing still, so you're not moving at all. The only time you can move is if the ship is not traveling at the speed of light. Now, the closer you're traveling to the speed of light, the more slowly the time inside your ship will pass. So somebody on the outside might see your ship flying by for a year or more near the speed of light and would measure that time on their calendar, but for you inside the ship, it may only take a second or two if you're traveling that fast. So time is distorted, and the more rapidly you're moving, the more distorted your time would be. It feels normal to you, but to an outside observer, you'd be moving very, very slowly. So the answer is no. You can't walk toward the front of the ship traveling at the speed of light and go faster than light. Here's also another very interesting from Annie K. And the question is, the sun's going around the galaxy, and it takes 225 million years for it to go around the galaxy. But what force keeps it moving? Where's the energy coming from that keeps the sun moving around? The answer is conservation of momentum. You see, space is frictionless, and once something gets moving, there's nothing really to slow it down. There's no influence to change that. Now, in the case of something in an orbit, it's simply following the curve of the space-time, so it goes around in a loop. And as long as nothing gets in its way or distorts the path, something hitting it or something deflecting it like another gravity field, it's going to continue to go around in that loop forever. So it is a frictionless medium, and nothing's going to slow it down. So the answer is the energy of movement was already there, and it's simply conserving that energy and following the path forever. Now, the technical name for this is Newton's first law of motion, that a body at rest will remain at rest, or a body in motion will remain at motion unless some outside force disturbs it. So the momentum, the force of movement, isn't lost or wasted or used up. It remains with the object permanently unless it's altered in some way by an outside force. That's Newton's first law of motion. Now here's a question I get from time to time. Stephen M. asks, is it possible to make a temperature lower than 0 Kelvin? And the answer is no. Let me explain something. When we measure temperature, we've decided, after taking all the measurements, the energy of temperature is molecular or atomic motion. And if you take an object and you remove all of that atomic motion, it becomes cold. In a hot object, it just means that the particles that the object is made of are moving very rapidly, but generally not rapidly enough for them to become a liquid like melt or become a vapor. If it's a solid object, the bonding of the atoms holding it together remains, but all the little atoms themselves are moving very rapidly. Imagine a bunch of rubber bands tying little steel pinballs together. And you have an object, and it's made of these steel pinballs tied together in a net of rubber bands. And you give the little steel ball a shake at one corner, and that shake spreads in waves through the rubber bands to all the other steel balls. This is sort of like the temperature of an object. And the more those steel balls, those pinballs are shaking, the hotter the object is. But if it's not enough to break the rubber band, then it won't melt. It remains solid. By cooling an object, you're removing all that molecular motion. And if the little steel balls are not moving at all, then it would be absolutely cold. Now, there is a caveat. There's a little rule here. Very cold objects don't completely and totally lose their molecular motion or atomic motion. The lowest possible temperature is 0 Kelvin. And to remove all of the movement of all the atoms and all the particles something's made of would put you at 0 Kelvin. Going below 0 would mean what? I mean, if nothing's moving already, then it doesn't have any energy for heat. So that's why 0 Kelvin is the coldest temperature. That's where all the intrinsic movement, everything has been removed, and the particles are only responding to the vacuum fluctuations, the actual noise at the base of space-time itself. Think of it as the noise in the basement. Now, there's a special case where if you remove enough of the movement, enough of the energy, and things get cold enough, they can reach a new state called a Bose-Einstein Condensate. This is a material that is so cold that the movement of the particles has pinned down their location, and suddenly it reaches a strange stage where it could violate something known as the uncertainty principle. We would know both the location and energy of the particle perfectly well. Well, when you try to do this, quantum mechanics steps in and does something very strange. Weird things begin to happen, and what happens is the particles no longer keep their location as, let's say, a little pinpoint. They start to smear out. They get fuzzy, like a wave instead of a particle. So at the very lowest possible temperatures, matter smears out into quantum waves and does very bizarre stuff, like being able to be in two places at the same time. We normally don't see these conditions. They can be produced in the laboratory, but they're extremely difficult to maintain. So even in that case, no, you can't go below 0 Kelvin. That's the coldest possible temperature, and that's why, because that's when it has no molecular motion. Okay, and here's one more before we go to our break. Peter Height asks, why do particles have rest mass energy? This is actually an advanced physics question, but it's an easy one. It's because matter is energy that has been condensed. So when we're looking at mass, mass is equivalent to a certain amount of energy. And so when we're talking about rest mass energy, we're just looking at if you took that mass and you turned it completely into energy, how much would it be? I mean, particles, mass, they are energy. And so mass and energy have an equivalent. That's the old Einstein equation everybody's familiar with. So we're going to continue with a lot more of these questions and answers very shortly. We're going to a break right now. This is Talk Universe, and anybody who has questions, call in, and we'll answer those questions. You can send them on Facebook, or you can send them to the Talk Universe address, the email. And let's get your questions on electronics and optics and rocketry and robotics. We've got a lot of really interesting material to cover here. This is Talk Universe. Welcome back from the break, and the questions keep coming. We have a really interesting one right here, and it is, why does metal conduct electricity? I love a good fundamental question, the ones that go right to the heart of the matter. Well, it's actually a pretty simple one. To first understand it, you have to know something about atomic theory, and atomic theory sounds complicated, but it's really simple. You look around you, everything you see is made of atoms. Everything in the world, everything you're ever likely to encounter is atoms. And atomic theory simply means that matter is made of tiny little discrete units. There are about 120 different types of discrete units, and they come in different flavors like carbon and oxygen and aluminum and magnesium and phosphorus, and they're called elements. Now, when we look at elements, when we look at atoms, they really have two components. They have the nucleus, which is where all the mass is located, basically, and then they have everything else, the electrons, which are in a cloud on the outside. And if you look at an atom, you'll find that the electrons are very tiny and they're very mobile, and generally they're pretty easy to knock off. If you're walking across a carpet on a cold day with rubber-soled shoes, and you scuff along, you're knocking electrons off and accumulating a static charge. And when you reach the doorknob and reach out and the spark leaps from your finger to the doorknob, then you know that you've done the energy, the work necessary to knock a lot of those electrons free and collect them. So you've made electrons rip off of those materials, and that's a spark of static electricity, for instance. Now, if you look at an atom, and it has one or two electrons on the outside that are easily knocked off, you've got a metal. Metals are atoms that have one or two electrons on the outer shell. So metals have electrons that are easy to move around. And when you look at a piece of metal, if you could super magnify it and see what's going on, you'd find that when metal atoms stick together into a crystal of metal, a piece of wire, a piece of sheet metal or foil, what you're really seeing is all those atoms are submerged in a sea, like a liquid of electrons that easily move around. So metals conduct electricity because they're surrounded by this sea of electrons that very easily can be moved. And that's why they are such good conductors, because a charge moves by moving little charged particles around, and those are the electrons. So metals conduct electricity because they have mobile electrons on the outer shells, and metal, by definition, is an element that has one or two electrons on the outer shell. It's pretty simple, really. Very simple. And if you think about it, it also explains what an insulator is. An insulator is just a material that has its electrons held pretty firmly, and those electrons can't move from atom to atom or molecule to molecule. They're basically static, unmoving. So an insulator does not have those mobile electrons, and therefore it cannot conduct electricity. And that's the basis of it, right there. Here's a good question that Emily asks. What is the densest element? That's a really good one. Now, a lot of people think of lead as being pretty dense, and gold is pretty dense. And those are pretty dense elements, but you might be surprised. The density of lead is a little over 11 grams per cubic centimeter, while the density of gold is over 19 grams per cubic centimeter. So gold is literally almost twice as dense as lead. So when you pick up a bar of lead and you think about how heavy that is, just about double that figure, and that's how heavy gold would be in the same size. The densest normal matter known is the element osmium. And osmium has a density of about 22.6 grams per cubic centimeter, nearly twice the density of lead. So that's really, osmium is actually more dense than gold. That's the densest normal matter. Now, some of the elements that have been manufactured on the periodic table are estimated to have densities as high as 40 grams per cubic centimeter, but nobody's made enough of it to actually verify that. But if you want to know the densest matter that has been made in a laboratory, at the Large Hadron Collider, the nuclear particle research facility, they have smashed very dense atoms together near the speed of light and created what's known as a quark-gluon plasma. And this isn't an element, but it's a very dense material. The density of this material is 40 billion tons per cubic centimeter, which, is a lot more than a few grams per cubic centimeter. But you're not likely to ever encounter this material, and you really wouldn't want to try and pick it up. It would be extremely hazardous if you could get anywhere near it. Now, Raul asked a really fascinating question. He says, is the Earth gaining or losing mass? Well, believe it or not, it was thought in times past that the Earth was actually gaining mass because there is material falling to us from space in the form of meteors, space dust, and other material. But when you look at the loss of water vapor and atmosphere, we lose about 50,000 tons of mass per year to space, and we gain about 40,000 tons of space dust and junk. So we're really losing mass a little bit each year. But there's nothing to worry about because the mass of the Earth outweighs that by many orders of magnitude. So we're not worried about the planet evaporating away or anything like that. But that's a very good question. And here's a question that actually addresses a little electronic issue. How does a memory chip store memory? That's actually a question from Thomas, and it's simpler than it sounds. In a microchip, you have millions and millions of tiny cells that are insulated from the surrounding material that they're made in. The chip is generally silicon, and so these cells are embedded like little tubs in the silicon, but they're just a few hundred atoms across. And these little tubs can change the charge they contained. So think about little Tupperware containers. They can be full of marbles or empty. And when you charge it up, you're putting the marbles in the container. Now, when you read the bit out of there, what you're doing is you're measuring that charge with a little capacitor. And so when you store the bit, you have a way of putting the charge in the little tub, the little container. And when you erase the bit, you're simply getting rid of the charge in the little container. So properly designed flash memories can be written and erased, thousands or millions of times without that tub degrading. In times past, they used to have to use ultraviolet light to do the trick, and they had a limited storage of about 15 to 20 years at best. Now the technology we have today is based on much better materials and uses quantum mechanical methods to get the charge in and out of the little tubs, the little storage cells. So each bit of memory represents a place where there's a little charge stored or no charge. And when you take 8 of those little charges together, that adds up to 1 byte of information. So all the memory devices that you use typically are arranged in 8 or 16 or some multiple of 8 numbers of bits strung together to represent a byte of information. And it's charged into this little piece of insulator similar to a capacitor. Here's an interesting one. Shivam, I suppose is pronounced, from India, asks, when a beam of light passes through colored glass, why does it change the color of the light? Well, actually what's happening is this. If it's a beam of white light, it's got all of the colors of the spectrum in it already. And when it passes through the glass, it is absorbing all of the other colors of the spectrum so they don't get through. Only the light waves that match the color of the glass can pass through it easily. And so what happens is it literally selects out only those colors. That's what makes it colored glass. It's absorbing all the other parts of the spectrum. So if you have a piece of green glass and you shine white light through it, the white light has red, yellow, blue, orange, green, all the different colors of the spectrum. The glass is absorbing the red and the blue and the violet and the yellow and letting only the green light through it. So it's really simply stopping a lot of the light and allowing only the color that's proper through the glass. Now, this question also brings to mind something that I saw a long time ago and when I was a kid, and I wondered about it, and I figured it out. And a lot of people have asked me the same thing. A lot of us have driven by old stores, and they have posters in the window that have been there for a number of years. And color posters tend to bleach out in the sun until only the blue ink remains on them. And I know we've all seen this. The colors lose the red first, and then the yellow and the orange. That all goes. Pretty soon the poster is just blue ink. And why would that be? Well, there's a very simple answer to that. And it has to do with the fact that shorter wavelength light, bluer light, is very energetic. And longer wavelength light, red light, is not so energetic. Now, the chemicals we use, the dyes in the ink, the colors on the posters, can absorb certain frequencies and reflect certain frequencies. So when you see red ink, it's absorbing the white light and it's reflecting only the red part of the spectrum. All the other light is being absorbed. When you see green ink, it's absorbing everything except the green and it's reflecting that. This is the exact opposite of the colored glass question. This is a reflection rather than a transmission of light. Now, the coolest thing about this is that blue light is extremely energetic. The red dye is absorbing all of the most energetic light, and it's breaking down the chemicals the red dye is made from. And so when you get to the orange, it does it a little less effectively. When you get to the green, it does it a little less effectively. Blue dyes are reflecting the blue light, the energetic light, and they're not being bleached. They're not being broken down. They're only absorbing the lower energy red and orange and yellow light that doesn't have an effect on the chemistry. So the blue dyes are the ones that don't get bleached out because they're throwing away the exact light that would destroy them, the blue light, the energetic light. Here's a similar question from Sydney in Philadelphia. He says, I had an old Chevy and the dashboard was made of plastic and the plastic was all cracked. Can you tell me why the plastic cracks over time? This is actually a very relevant question. A lot of people think of plastic as being permanent, and it really isn't. Sunlight does degrade plastic, and we've all seen it, particularly in the old cars that had plastic on the dashboards and things that have been exposed to a lot of sunlight. This is because sunlight does carry a measure of ultraviolet in it. And the ultraviolet has two effects on plastic. When sunlight with ultraviolet is shining on a plastic object, the first thing that happens is the ultraviolet breaks down the plastic molecules, similar to the blue light bleaching the posters. The ultraviolet and the blue light, the shorter wavelengths, are very energetic. They break some of the bonds in the plastic and make it brittle. So it's basically eating the plastic molecules apart. But there's a second effect that a lot of people don't take into account. This is that when the ultraviolet light is shining through the air, our air has a lot of oxygen, and a tiny amount of ozone is being generated by that ultraviolet light. Now, ozone is an aggressive bleaching agent and an aggressive attacker of organic molecules, such as plastic. So whenever you put that armor material, the oily guard material, on the plastic parts of your car, like the dashboard, what you're doing is twofold. You're putting a material that's a sacrificial material that the sunlight and the ozone cannot degrade very easily. You're shielding the ozone from reaching the plastic and the sunlight from reaching the plastic. It's very much like a sunblocker, so that's why those compounds work as well as they do. So now this takes us to an astrophysics question next. Usama L. asks, why can't we find the center of the universe? That is actually a very interesting question. When we look at the sky around us, we see that the stars in the galaxy seem to be pretty uniformly distributed in all directions. Well, the answer is very, very simple. If you look at a balloon and you're on the surface of the balloon, walking on the surface, you'll never reach the center. The center is actually off of the surface of the balloon. The center of our universe is off of the surface of the universe. It is backwards in time, almost 14 billion years. It's at the center of the balloon. You can't reach it. We've expanded away from that point. And the galaxies are like painted on the surface of the balloon of space-time that has expanded for all these billions of years. So that's why you can't find the center of the universe. You're looking up the skin of the balloon and not the center of the balloon, the volume in the middle. And that direction, if you were trying to point in that direction, is the past. This is why people talk about time travel, because there is another direction that you can't reach into, this fourth dimension, and that's where the center of the universe is located. That's why you can't reach it. It's literally out of reach. Now, Shecky has an interesting electrical question. He says, there's a bird sitting on the wire, the power wire outside, and it's not getting shocked. Why is that? Shecky is very simple. The bird is on one leg of the electrical circuit and not grounded. So there's no path for the electrical current to go through. The bird can't be shocked because it's not making contact with two ends of the circuit. There's no power and ground. So the bird's safe. But don't try this at home, please. We'll be back with more questions and answers on Talk Universe in a little while. Settle in and send me some questions. We'll enjoy answering them here live on the air. This is Talk Universe. And the questions keep coming. We've got an interesting one from Mel Talent, and he says, I'm looking at clouds and I see thousands of tons of water, according to the internet, suspended in the air. Is this due to electrostatics? No, actually it isn't, and thank you for the question, Mel. Basically, the droplets in a cloud are suspended due to drag forces in the air. The amount of mass of a drop of water is so tiny that the random movement of the air can keep it aloft. I mean, we've seen dust particles suspended in the air, and the water droplets, the mist in a cloud, those droplets typically are smaller than dust particles. And so you can imagine that with a little bit of updraft, that water can remain suspended as long as it's spread out thinly in those tiny droplets. They have a lot of surface area and a lot of drag. Now, here's another thing, though. You mentioned electrostatics. What is very interesting is that when all those droplets have the same charge, they slightly repel each other and they remain unconnected. But when a lightning stroke reaches the ground and that charge dissipates, this actually can allow the droplets to come together and form raindrops. So the electrostatic element that you mentioned has nothing to do with keeping the clouds suspended, but it can keep the droplets from coming together to form actual raindrops. And so this is one of the elements why we see lightning associated with rain quite often. But it also has another effect. I wrote a paper many years ago called Cosmic Rays, Lightning, and Life. In the paper, I pointed out that cosmic rays, charged particles from space, actually create charged pathways in the atmosphere when they smash into the air atoms and explode them. And those branching pathways are the pathways that draw the lightning through them. So the branches of lightning are caused by cosmic rays. And those lightning bolts branching through the air actually burn some of the nitrogen in the atmosphere and convert it into a nitric oxide, which goes into solution in the rain. And this is where the nitrates come from to fertilize the plant life on Earth. That 90% of the plant life on Earth wouldn't be here if it weren't for lightning and rainstorms and cosmic rays. What an interesting connection. Here's a question from Greenville 5, a little more astrophysics. How many stars are in our galaxy? Estimates have changed over the years, and up until recent times it was expected to be 100 billion. Recent estimates have moved it up to 200 billion, and it may be as high as 400 billion stars. A lot of people are comfortable with a number in the middle, somewhere around 300 billion. So we're not exactly sure because a lot of the stars are small and difficult to see. Some of them are brown dwarfs. But it would be safe to say there's roughly 300 billion stars in our galaxy alone. Here's a question that obviously is nuclear physics, and it's from Barnhart 12 in Pennsylvania. We get a couple of questions from Pennsylvania lately. His question is, can neutrinos actually move faster than light? Actually, no. In the news a couple of years ago, there was a lot of flap about some neutrinos being clocked as faster than light. And actually, this wasn't true. It turned out that there was an error in the time measurement system that made it appear that they were moving faster than light. So, no, neutrinos are normal matter, and they do have some mass, and so they can't travel even at the speed of light, much less faster than light. However, there's a theoretical particle that's never been detected called a tachyon, and nobody's really sure if it's real or not, but it would be defined as a particle that always moves faster than light. And if such particles did exist and we could use them, it may be possible to send information into the future or receive information from the past, for instance. But again, this is just a theory. Nobody has actually ever received or sent tachyons or knows even what their properties would be or how we would interact with them. So that's all theory. Melanie from Arizona says, is Pluto actually a planet? This is kind of a controversial thing. You have to know where the definition of the word planet came from. When we have a word such as atom or, something of that sort, we know exactly what it is. It's a measurable fixed quantity in the world. But then, let's say you have a piece of chalk and you break it in half and you have two pieces of chalk. But that doesn't mean you have more chalk. We simply define it as a piece of chalk. A planet comes from an ancient word, planeto, which means wanderer. And so a planet was simply a dot that wandered in the sky. And people didn't know how big or how small it was or how far it was or what it was made of. It was simply a moving dot of light. So when we go to try and attach an ancient name to a technical description, it can be very confusing. The International Astronomical Union came together and made a decision in France a number of years ago that it was not a planet, and they did this by saying, well, and this was sort of arbitrary, they said, well, in order to be a planet, it had to have a couple of characteristics, and one of them was that if it were a molten droplet, it would solidify as a ball. If the planet were able to circularize itself or make itself a sphere under its own gravity, then it was a ball, and then it was a planet. And if this body also had cleared its orbit of other debris, such as asteroids and other materials, then that also strengthened the definition of planet. And finally, that it had to be 1,000 kilometers or more in diameter. So by those definitions, no, Pluto isn't a planet, but it is a world that you could go to, and we actually have a number of other such worlds in the dark, cold recesses of the Oort cloud of the Kuiper belt that orbit our sun. We might have another dozen or more planets out there that are, capable of fitting that description, but we haven't seen them yet because they're so distant and cold. They're very, very difficult to resolve because there isn't enough sunlight illuminating them to see them very clearly. So how many planets are in our solar system is not a resolved question at this time, but it's a fair bet that there are at least a couple more that we're not aware of. Here's a good one. Carly in Brazil says, what is an organic molecule? That's actually a very good question because there are molecules that are found in organisms that are produced by the organisms, and they're clearly organic. And there are other molecules that, by definition, we might think of them as organic, but they're not. Typically, an organic molecule contains carbon, because without carbon, you can't make any of the compounds that life requires, really. The thing is, carbon is a very flexible atom. It's got 4 bonds, and it can stick together in a lot of different ways. So, as a general rule, if the molecule has carbon in it, it's an organic molecule, but there are many molecules that have carbon that aren't organic at all. Like, give you an example, silicon carbide, definitely, or titanium carbide, that wouldn't be an organic molecule. So it's easier to say that it generally will have carbon plus hydrogen, oxygen, and nitrogen, or some of those atoms together to make it organic. If you look at any of the alcohols, carbon, hydrogen, and oxygen would be found in any alcohol molecule. But when you talk about organic molecules, typically it's going to be, think of CHON, carbon, hydrogen, oxygen, nitrogen, and you're going to be real close to target. Now, there are a lot of organic molecules that have never seen the inside of a living organism. Many organizations define methane as an organic molecule, but most of the methane in the universe is not from organisms. It is simply from the random carbon and hydrogen that's free-floating in space. So organic is kind of a slippery definition, but again, a good general rule. If it has carbon in it and it also has hydrogen, oxygen, or nitrogen, then it's probably an organic molecule. Your Alexander from Chicago has an automotive question. It is, why does cold air going into my engine seem to make it run better? It's very possible that your engine, like a lot of the older engines, doesn't have any of the digital controls in it. Cold air is more dense, and so a given volume of it will have more oxygen. In most cars that are high performance with a supercharger, what they're trying to do is pack more air pressure into a given volume, and therefore you get more oxygen per unit of air brought into the engine. But cold air is dense, and it has a higher density, and therefore more gas molecules will fit into it. Cold air and superchargers perform a function known as increasing the volumetric efficiency. And that's probably exactly what's happening. And yes, it does make your engine run better. Here's one from an Eric J. 2004. And the question is, I have a relay, and when I connect the terminals of a battery to it and then disconnect them, I see a spark. Why is that? Well, this is an interesting thing. A relay is an inductive device. It's a magnetic coil. And when you attach power to it, the coil literally charges up a magnetic field around itself. And when you disconnect the battery from it, that field doesn't simply vanish. It has to go somewhere. When the field collapses rapidly, it induces a voltage in that coil that contains the field. And that voltage can actually be 1 to 200 volts or more sometimes. So this is one of the principles behind spark coils. And the inductive effect is that the coil that created the field and maintains it when power is removed actually becomes an inverse transformer. It converts that collapsing field back into a high voltage, and that's where that spark is coming from. Something that a lot of people aren't aware of is that small DC or slot car motors can actually generate a couple of hundred volts of electromagnetic noise and can actually blow out the semiconductors that are driving them, a transistor driver circuit. And so you design them with a diode to shunt that excess voltage back to ground and prevent damage to your circuit. There's an art to designing high voltage drivers and even low voltage drivers. And all of the toys and drones and little robots and things that you see, printers, all of those things with motors in them have to have this sort of clamp circuit built into the drivers that run the motors. And incidentally, if you have a DC motor and you spin the shaft of the motor, if it's a permanent magnet motor, you'll find that you're generating a voltage by spinning that shaft. And a lot of people use DC motors as generators. This has practical applications in your car. If you have a hybrid car, then it has hub motors that can drive the wheels electrically. But when you are braking, you actually can use the power of that spinning wheel to regenerate part of that power to go back into the battery and actually provide braking for you. So the energy of braking a hybrid vehicle can actually be used to recover about 40% of that power and get it back into the battery when you're braking, which is a very useful thing. Now, we had a scheduling issue with the show we originally were going to run tonight, and so we were unable to interview our guests, and that was part 3 of our Mars series. We will get back to that hopefully in the coming week, the next week. And so we're going to have some very interesting information about NASA and the European Space Agency and their involvements in the search for microbes, endolithic organisms. We'll go into that in a lot of detail in the upcoming show. And also, I do have a book recommendation. This is an older book and one that might be a little tough to find these days. And it might sound a little offbeat, but trust me, it's a very good read. It's called Zen and the Art of Motorcycle Repair. Look it up. I think that you'll find it extremely helpful and entertaining. And it isn't a technical book by any means, but it's more a way of thinking and a philosophy. And I think it could be something that a lot of people could benefit from. The world we live in today has a completely different picture of how we live and how we should live, and how things work and how we perceive them. This is a good book to give you, let's say, a little bit of a different perspective on things, a calming perspective. Now, we had a lot of interesting response from the drone program that we did last week, and I briefly appeared, for a couple of hours on Coast to Coast recently and did a robotics program, and so there was a lot of interesting material in that. I think that the interest warrants a more in-depth show about robots and drones and AI in general. We'll get to that. We're also going to get through our gene-tailored organisms, but the coming show that we do after our Mars series will be Clean Water Everywhere, and this is a show specifically looking at the supply of fresh drinking water in the world and its importance to our life in general. We're going to cover a lot of issues, and some of them I'm sure will be hot buttons for a lot of people, and we'll look at the water supply on Earth, where it's going, where it came from, and what we can do to improve it. This is one of the most essential things we know. The existence of life is very, very tightly coupled to the presence of good water, and without that, you can't have crops, you can't have agriculture, and life as we know it would really dry up and die. We're going to cover this very sensitive subject and see what can be done about it. Meanwhile, I always go back to the scarcity is a myth thinking, and I want to stress that. I've had a lot of support from listeners to the show, and I really enjoy doing these shows. I'm looking forward to more feedback, and we have many more interesting shows coming up soon. Remember, scarcity is a myth. We have everything we need to create everything we will ever need. And just take a time sometimes to sit back and appreciate the things we have. I know that things have been really wild in the world over the last couple of years. It may calm down soon. We'll see how that happens. Meanwhile, I'm your host, Sir Charles Schultz. This is Talk Universe. Have a wonderful evening, and thank you for listening.